I always give out these 3 books, so don't worry. This was going to happen anyway. And in this book, you would find a more detailed treatment of these models that we're going to recap today. And there will be no breaks today because we used a lot of the time to discuss homeworks and non-lecture related topics. All right. So the first neighbor that we're going to talk about is the nearest neighbor classifier. And the nearest neighbor classifier is a very intuitive model and it's very easy to explain. How many of you, I don't know how this is said in Vietnamese as a language, but in my language, there is a saying that the old people used to say, and it goes like this: if you show me your friend, I will tell you who you are. Is there a way to say this in Vietnamese? If you show me your friend, I will tell you who you are. So maybe Jessica, okay, Anne, please. And Larry wants to, can you tell me how to say that in Vietnamese? I mean, I cannot say it, but you know what I mean.
I think it's like gần 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 mực thì đen, gần đèn thì dạ. Like when you're close to ink, you'll be dark, and when you're close to the light, you'll be shine.
Exactly. Fantastic. So this is it. That's nearest neighbors done. That's the explanation for nearest neighbors. Whoever you are close to, that's who you are, nearest neighbor. So if you're close to the plus side, your label is going to be plus. If you're close to the negative side, your label will be negative. Like Anles said, if you're close to the light, you're light, and if you're close to dark, you're dark. That's the idea. But the way and we can use this model as a classifier also as to solve a regression problem. And you would see that for us to, but for me to, now I have a question for you, Anle. For me to be able to say that you're close to someone, what do I need to be able to, what do I need to have in my domain? There is something I must be able to calculate before I can say whether you're close or far away from something. What is that, Anle?
I think it's number of people. Like
Yes,
100.
that's important. But for me to be able to say if I am close or far away from you, there is some distance. That's it. This is the central idea to me being your neighbor. If I can calculate distance, then I can say that you're my neighbor because the distance is small. And when the distance is far, then I can say you're not my neighbor. So it makes sense that the central idea in nearest neighbors is this notion of calculating distance. Whether I'm trying to use this as a classifier to just determine whether I am plus or minus, or tall or short, or I'm trying to use this to solve a regression problem, I have to be able to calculate distance. I have to be able to tell whether or not some data point is my neighbor, right? So, and of course, before we go through this example, a lot of this would happen in the training space, right? In the data space, in the problem space. This is really the input space, right? So the final thing I would like to say is that there is also like an implicit notion that if you're my neighbor in the input space, in the X space, then whatever, when we come out, okay, we go through the processor system and the output, we would also be neighbors, right? That's the final thing you need to know. So if we're neighbors in the input space, meaning that x1, x2, x3, if x2 is the neighbor of x1 and x3, then when we get to the output space, y1, y2, y3, they will always also be neighbors. So there is this expectation that this assumption holds in nearest neighbors. And this is very powerful because when you give me an input, to be able to determine what it is, all I have to ask is, what's the neighbor in the input space? And if I know what the neighbor is in the input space, I can determine what the neighbors are in the output space. And if I find the average, then I know precisely what it is. So And again, and I just explained to you the complete intuition behind nearest neighbors. One is who your friends are, is who you are. Two is being able to calculate distance so I can determine who my neighbor is and who is not my neighbor. Three is if I'm your neighbor in the input space, then I'm going to be your neighbor in the output space, such that you can give me any arbitrary input and I can predict what it's going to be, what the output should be, right, using nearest neighbors. All right, so let's now use this IDR to solve a classification problem, and we would just run. We would run with a data point that has three features or three attributes or three columns, right? So in the first attribute is a binary attribute. It's either yes or no. And in the second attribute is about size, so small, medium, or large. And the third attribute is about money or some big quantitative attribute. And but it's actually money. So 125K, 100K, 70K, 120K, 95K, and things like this. And based on some nonlinear algorithm, right? There is a nonlinear decision boundary. We would classify you as no, or we classify you as yes. And you can say that, for example, this could be saying yes or no to a loan application. If you said yes to being married and you said yes, you said you're large and you make 125K, well, we're not going to give you a loan. But if you're not married and you're large and you make less money, we would suddenly give you a loan. So clearly there is a non-linear decision boundary here. So in fact, I will take this opportunity to also share my other screen and show you something. All right. Okay, so how many of you have seen this picture before? Maybe somewhere, just a picture that looks like this. Usually when you're looking at a lot of machine learning algorithms, you see this wiggly line. How many have seen this before? If you've seen this kind of wiggly line related to machine learning, no one? Okay. Well, the difference between this red line and this wiggly line, Jessica has seen this before, is the decision boundary here is not linear. It means that, for example, I will give you two examples. There is the example that we're looking at right now of using three attributes to determine whether or not I'm going to give you a loan. And there is what I would just say that if you make more than 100K, I would give you a loan. That's a linear decision boundary because everything to the right of this red line is loan. And this red line is the division, is the dichotomy. That model say only ask one question, do you make more than 100K? So anything more than 100K and $1 would be to the right of the line, and 100K and less would be to the left of the line. So this is a linear decision boundary. It's just a simple question. If you make more than this, you are on the right, and if you're less than this, you're on the left. If you're taller than 6 feet, you're on the right. If you're shorter than 6 feet, you're on the left. And if you're at 6 feet would be literally on the line. So how do you interpret that? That's for another day. But when you look at this decision boundary, it's not one question. You can see that this line wiggles. It's a wiggly line. And usually when you see machine learning models, they are trying to figure out this nonlinear decision boundary. We're not using one question to determine the outcome. We're using a series of questions to determine the outcome. So the decision boundary is nonlinear. The decision boundary is, in fact, a wiggly line. So this is the point I'm trying to make. So in fact, the decision I'm trying to learn or to hear, right? Because your model has to learn from the data. And the way it works, of course, is you would give it a bunch of data and you will give it the answer. This is called the example. And based on this example that you've given to it, you want it to be able to solve a general task of the problem. That's generally how supervised learning works, right? But a lot of the things that we do in the real world is supervised learning, meaning that we do learn from examples. We learn from the data. So we're not going to talk about unsupervised learning in this class. So that's the prevailing assumption that we are learning from examples, we are learning from the data. So we've got to supply a bunch of examples, then we see how the model performs when we give it a questions to solve. So you can kind of think about what is going right now as training, right? I give you a bunch of examples, then I give you a homework. And I say, well, go solve the homework based on the examples I gave, right? So this is precisely what's going on in machine learning as well. Is I give you examples, then I give you homework. Okay, so the decision space described by my example, right, in this 3 attribute space is definitely not linear. It's not a simple line. It's a wiggly line. It's a nonlinear decision boundary that I am describing in the example that I've provided. Whereas if I was just checking how much money they were making, it would be a line. The decision boundary would be a line. That's what my example would describe. In fact, I don't even need a data science model for that. I can just write a simple program. If it's less than 100K, deny them, right? So, and if I supply the data, the model will be able to determine the same straight line from the example you've provided. So it doesn't matter whether you don't need to say it, but if you provide the data where you reject everyone lower than 100K, the model would know that everyone lower than 100K should be denied and everyone above 100K should be approved. It will also be able to figure out that the decision boundaries, of course, linear. So this is the triumph of these data models, that they can learn from examples and form general hypotheses that they can use to solve problems in the real world. So back to what we're discussing in this case. So we have the 3 attribute problem, and in our very first example, the person said yes, and they were large and 125K, and the class is no. We denied the loan. And the next person said no, medium, 100K. We also denied the loan. The third person said no, small, 70K. We denied the loan, right? And the next person said yes, medium, 120K. We also denied the loan. Now the next person said no, large, 95K, and we approved the loan. So there is something to be said now. So let's jump to number 8. Number 8 also said no, small, 85K. We also approved the loan. And it's beginning to look like for you to get your loan approved, you at least have to have no. But that is not the only requirement, because there are other people that said no and they got their loan denied. But there is no one who said yes, that got their loan approved. So, and if you go to the last person who got the loan approved, they also said no, small, 90K, and they got their loan approved. So let's look at the people who got their loan approved and look at attribute 2. So we can also find out that it doesn't matter whether you're large or you're small. Whether you're large or small, you could be large or small and you could get your loan approved, right? We cannot say anything about medium, because no one got their loan approved that was medium, but we know that you could be large or small, you could get your loan approved. And we also know that based on this example, you have to say no to get your loan approved. And it doesn't really matter if you're large or small. We don't know about medium, but it seems like it does matter. It does. We also know that you have to make at least 85K, right? We know you have to make at least 85K because why do we know this? Because of number 3. If you look at number 3 was no, small, but they were making 70K and they got their loan denied. And number 10 was also no, small, but the only thing that changed is they were making 90K and they got their loan approved. So we know that you need to make more than 70K. That's for sure, right? So we know you need to make more than 70K. So yeah. So now you can see that the decision space is not linear. It's not a simple line anymore. There is a combination of factors that we have to consider. You have to have not just one correct answer. It has to be correct, across 3 attributes, and then we can approve your loan or not approve your loan. So based on these examples that we have now we teach to our model, the model learns, right? There is a learning algorithm that the model uses to learn and update its coefficients, right? Because these machine learning models, they have coefficients, weights and biases that they are updating, which is how they represent what they have learned, right? And now we apply the model on this real world problem called the test set. So there is the training set, which is your example, and there is the test set, which is the real world problems you want the model to work on. And that's how you determine what we call your out of sample performance. So this is your training set. This is the examples. And out of sample performance is how the model performs on the real world problems that is not included in the examples, right? Because if I simply give the model these problems in the examples, it will just tell me what the answer is because it's memorized them. And the more there is a problem in machine learning called overfitting, where the model simply memorizes the examples and it does not really know how to solve these problems in a useful way. Just memorize the example. We call it overfitting, right? So and there are ways to prevent that. But whether it overfits or not, if you ask the question, if you select a question from the training set, it's more likely to give you the right answer because it's seen it before in the training set. A true test of the generality of the model is how well it performs on a neutral set of problems called the test set. So now when we look at 11, when this guy said no, small, and I am making 55K, well, we kind of know that it's not going to approve this loan because it is smaller than 70K, and we know that you need more than 70K to get anywhere. We don't know precisely how much you need, but we know it's more than 70. So it's easy to solve this problem. And someone said yes, medium, and 80K, and we don't know what the answer is here. So, but it looks like it should be a denial. Someone said yes, large, and 110K, but there is no example where someone said yes and they got their loan approved. So it seems like this would be also denied. And number 14 is no, small, 95K. And when you look at our training set, it's very likely that we would approve this because we have an example that says no, small, 90K. And when you combine this with no, small, 85K, and you combine this with no, large, and 95K, it's reasonable to think that no, small, 95K would be approved as well. No, large, 67K, we don't know. Well, no, large, 67K, it's unclear what will happen in this case. We know that no, small, less 70K or less would be denied, but we don't know what the impact of large would be on that decision. But this is just a way of kind of showing you how these models try to determine what to do. So one thing you can take away from this also is that the more the examples you provide, the better the model will be able to perform. The more scenarios you show it, the more it would know what to do in when it sees other things in the real world. Now, what happens in these cases, you might ask? What would the model do? Well, it depends on the kind of model you're doing. All right. So nearest neighbor generally would say, well, this sample is close enough to a no, depending, like when you think about plotting a point in, imagine that this is a point on a graph, right? If it's a point on a graph, this no small 55K is going to be very close to no small 70K, and it's going to determine that it's a no. That's how nearest neighbors would do this, right? But there will be other models that will try to calculate the likelihood of this data point being in class no versus the likelihood of it being in class yes, and it will select the category that maximizes the score, right? So that's another kind of model which we're going to get to later on. So the way we figure out this problem depends on the model we're using, and for nearest neighbor, we just try to determine what the neighbor is, and what the neighbor is how we're going to assign these classes, period. Okay, so the idea of nearest neighbor, I've already said, if it walks like a duck, quacks like a duck, then it's probably a duck, right? So that's that. So here is a better picture for you to see nearest neighbor. So in the 3 example problem, and so how many of you have seen a graph before? A graph where you plot X and Y? If you've seen a graph where you plot X and Y, can you raise your hand? Okay, good. Everyone has seen a graph. Well, only, okay, good. You've all seen it, you know what a graph is. Good. You can put your hands down. So how many of you know that you can plot any number of dimensions? You might not be able to visualize it, but technically, I mean, theoretically, if you can plot X and Y, you can plot X, Y, and Z, and you can kind of visualize in three dimensions, but you can essentially have points that have n dimensions. You can have a point in a space where you have 10 dimensions, 50 dimensions. How many of you can think about that? You can think about that in your mind. If I can have a point with 2 dimensions, I can have a point with 3 dimensions, and also there is a universe where there is a point with infinite dimensions. How many of you find that interesting, or can you think about that in your mind? Okay, interesting. Only 8 people can think about higher dimensional space. All right. So let's do a practical test right now. Okay, this is not a test where I would score, but everyone can see the screen, right? So we're talking about neighbor, right? We're talking about this neighborhood. So I would take a screenshot. I would have to escape this and take a screenshot to show you an interesting point. I think this point is useful, is why I want to show it to you. So you can still see my screen, right? I want to use maybe purple. Okay. So how many of you can see this dash that I drew a purple line around? You can see it? Okay, very good. Imagine that right? So imagine that Jessica is this line, and here, this is sun right here. Okay, this is a 2-dimensional plane, and this is sun. Sorry, this is Jessica, and this is sun. Do you think that Jessica over here can see sun? Do you think that Jessica can see all the way to sun over here? What do you think? Jessica, I will let you answer that question. If this is you right here, and this is sun, do you think that on this two-dimensional plane, do you think that you can observe sun all the way over here, Jess?
I guess no, because there are the points between these two circles.
Exactly. Fantastic. This is a critical idea when you think about dimensions. This is a two-dimensional space. And in this two-dimensional space, this is Jess and this is sun, and there are so many points in between. So Jess cannot see sun. Interestingly, this is a three-dimensional universe. And I also cannot see you guys because there are so many points in the way. There are mountains, hills, oceans, there's variation in geography. Impossible for me to see you. But can you see, if you're in 3-dimension, right? If I add another dimension to this problem, right? So can the point or the object in 3-dimension, can the object in 3-dimension see? So there is now an object in 3-dimension, right? Right here. There is this object in 3-dimension looking at this plane. This object is able to look at this plane because it has a 3-dimension, so it has height. Do you think this object in 3-dimension can see both sun and Jess? That's another question for you, Jess. Jess, do you think this object in 3-dimension can see both you and sun?
I think not clearly, because there are still points between that red circle to the both.
Yes,
two
but
purple
this is a 3-dimensional observer. This observer is not in 2-dimension. So this dimension has the benefit of an added dimension. So this dimension is looking down at the plane. Do you think it can see both of them?
Oh yes, they at that point can see both.
Absolutely. So there is something I want you to take away from this, is the 2-dimensional plane is completely flat in 3-dimension, such that a 3-dimensional observer is able to look down at a 2-dimensional plane. So here is where I'm really going with this. So now think about all right, look at this. So this is, okay, so this is a plane. It's a plane because this is Y and this is X. So this is a plane. So think about just any line, and I would go back to the line here to make my point very clear. So this is the plane, and think about just any line here, and I wish I could change the color of this line so that, but I would like to change the color of this line. All right. I did change the color, but it's not working. Okay. Anyway, so this is my Y and my X plane. This is the plane. So there are 2 points, and any this is a point, this is another point, just a bunch of points in this plane, right? A bunch of points in this plane. right? So every point in this plane has two dimensions. That's both an x and a y component, right? So here, there is a x value and a y value. But look at this line on the plane. What do you think it's the relationship of this point on the plane to the line? Do you think this point on the plane is looking down at the line and can see everything on the line? Another question. Maybe Anler wants to answer this time. Phone, yes, please. What do you think?
Yes, I think this point can see everything on the line.
Exactly. So can you see where I'm going with this? So when the points in 2 dimension having x and y, they're looking down at the line. The line has 1 dimension. You can only go forward or backward, right, on the line. So 2 dimension is looking down at 1 dimension, and we just showed that 3 dimension is also looking down at 2 dimension. So 1 dimension is flat in 2 dimension, 2 dimension is flat in 3 dimension. Don't you think that this continues? So 3 dimension is flat in 4. So imagine, and this is just something for imagination to think about. Imagine there is a race of species that have 4 dimensions. Do you think they will be looking down at us in 3 dimension? Yeah, that's exactly right. They will be looking down at us in 3 dimension. We will be completely flat in a 4-dimensional universe. So we don't know how many dimensions actually exist on this Earth, but string theory has been able to demonstrate that we can have as many as 11 dimensions. And if this is actually true, that there is a 11-dimensional region on the Earth, then they will be seeing everything we're doing here, because we are just in 3 dimension and it will be completely flat. And it makes sense that this is an idea. The mathematics makes sense in a way, right? This flattening of dimension when you keep going to other dimensions. So points have a point in 4 dimension would look down on 3, a point in 5 would look down on 4, 3, etc. So, and I've kind of said this so that you can have a way of thinking about your data as points on a plane. If you have a data that has 5 attributes, well, it's a point on a 5-dimensional plane. If you have data that has 15 attributes, it's a point on a 15-dimensional plane, right? So when you have that idea, this flat picture that you're looking at right now, it's just representing a picture on a plane. So of course, it is being represented by a 2-dimensional plane, but you can just extend it to any plane that you want. This could also be a point on a 50-dimensional plane. So he's saying that if there is a point on this plane, and this point is close to a bunch of labels plus, according to nearest neighbor, this point will be classified as plus. Because on that plane, there is a distance metric that is defined. So look at what nearest neighbor requires us to do. It says there is a distance metric, meaning there is a way for us to calculate distance. Usually, the distance metric that we use is Euclidean distance. And because Euclidean distance has a very precise way of doing it, it's essentially a square of all of the vector components or the number of dimensions that you have, and then you would raise it to 1 over n, which would be the dimensions that you have as well. So you would square. So if you have a 5-dimensional vector and you have 5 numbers, you would square all the 5 numbers, you add them together, and you will raise it to 1 over 5. And that would be, in some sense, the length of the vector, and also a way of the length of the vector, meaning its distance from origin, right? So if you have 2 vectors, you want to determine their distance, then you would subtract it, right? You subtract, it will be x1 minus x1 at component I minus x2 at component I. Then you would continue like that, and when you find the difference, also you will add them together, and then you raise them to the power to 1 over n, which is the number of dimensions you have. So that's how you calculate Euclidean distance. It's very simple, and I would show you the actual formula, but it is So let's do that right away. So you have P and Q, which are 2 points on the plane. And so they have to be, of course, if they are on the same plane, it means they have the same dimension, right? If this is 5 by 1, this is 5 by 1. So you have to subtract them at the level of the component. So if you are talking about the first component minus Q, the first component, P, the second component, minus Q, the second component, you square it all, which gives you positive number. You add it together, and then you find the square root. Sorry, you don't raise it to 1 over n, you raise it to 1 over 2. You find the square root, and that's the Euclidean distance. So that's how to find distance in any dimension. So it doesn't really matter what this dimension. This could be 50 dimension, right? It could be 100 dimension. You would just do the same thing. You would subtract from the same position, from the first position, second position, third position, all until you get to the last vector component. You would square it, add them all together, and raise it to half, or find the square root, and that's the Euclidean distance. So there are other distance metric that you can use as well, but this is the simplest one. This would work in any dimension. It doesn't matter how many features you want to consider in your model. You can always calculate the Euclidean distance this way, right? So, but of course, all your vector components have to be numeric. All right, so let's quickly see the final point in nearest neighbor is when we talk about nearest neighbor, we always say k nearest neighbor. We say k nearest neighbors because it determines what is the size of the neighborhood, right? So for example, let's go back in our slide. So in this example, there is this kind of circle that is being drawn. And the idea is, well, this is an implicit neighborhood. But imagine that this circle is not there, right? So you could say that the neighborhood is the entire sample space, right? Like everybody's my neighbor. But then you will find that your model doesn't work as well. If everybody is your neighbor, then if everyone is your neighbor, the class that is the most common is what wins all the time. Does that make sense? If everyone is your neighbor, so think about this as whether or not you are. So let's think about male or female in the class, right? Distribution of male and female. If everybody is your neighbor, the model will predict who is more popular. If there are more men in the class, then the model will always predict men. If there are more women in the class, then the model will always predict women, because the entire data set is your neighbor, and we determine who your neighbor is by what's around you. So the class that is the most common around you would always win. And since you are using the entire database, then the model will be essentially useless, because it will always predict the winning class, meaning the class that is most common in the database. So this is why it is important for us to define our neighborhood. Like, how many data points do we want to consider in a neighborhood? Because you have to consider, so in this case, it is easy for us to say this is plus, because everyone in the neighborhood is plus. But imagine that in your neighborhood, you have both plus and negative, right? How do you determine who you are? Well, we have to hold an election, and the winning class is what we predict to be your class. And you can see that in this example, in this screen. In this neighborhood, this is X, which is our unclassified input. And around X, we have 2 pluses and 1 negative. So we predict that S is positive, right? Because we conduct an election and we say, well, there are more positives than negatives in this neighborhood. So X by default is predicted as positive, right? Because it's nearest neighbor. We go by what is happening in your neighborhood. And so we have to define what is the size of the neighborhood. If the neighborhood is our entire data set, then the model is useless, because it simply predicts the class that is most common in the example that we provide to the model. And but look at this. Look at this. In the second picture, there is one negative, one positive, and there is the unpredicted. There's the unpredicted class. So which one is it, right? There is a tie. So this is trying to tell you that you should consider an odd number of neighbors so that you can always break the tie. In this second example, this is a bit more complicated because this is even number and there is a tie. And so I don't know what to do, right? It's a bit ambiguous because I'm doing nearest neighbor and I have one neighbor negative, one neighbor positive. So I need to break the tie. And in the final picture, my neighbor, I have only one neighbor, so I am negative. You can see that this model is also not going to be great because you really want some confidence in your prediction. So you want to consider more neighbors, but not the entire data set. And there are so many ways. There are so many pictures that are closer to each other, such that you can draw this circle in so many ways. And depending on how you draw this circle, it could be minus or positive. So in those kind of examples, in this one, it's probably really likely that this x is negative. But imagine that there are more data points and it's very close together, and you can really draw the circle in a number of different ways. Then it will be unclear what this sample is and the correct classification. So the point is that the number of your neighbor should not be too large and it should not be too small. It should just be just right. So then that begs a question: how do you determine the k? Is there an optimal k that you should use? Well, this is an interesting problem. There is a way of determining the k called the elbow method, which allows you to calculate the amount of k you need based on the data size, based on the data set that you have. All right, so you can kind of see that this is the extreme example where you have one nearest neighbor, meaning the k is 1. You're only considering one neighbor. You can see that there is many dichotomies in this example, and this is really poor because it's really hard to classify an unknown sample when it falls into a really weird region. You don't know which one it is. Depending on how you draw it, you can end up in a number of different categories. All right, so we already talked about the distance metric being Euclidean distance, and you would subtract, right? So it doesn't matter whether it's P first or Q first, it doesn't matter because you square it, and whether it's P or Q first, if you square a negative number, it becomes positive. If you square a positive number, it becomes positive. So we're only interested in the difference. So you subtract two vectors and you do that. You've already done the vector algebra. You know you have to subtract the components. And then you add it together, meaning that imagine you have a vector 2, 3, and another vector 3, 2. You would say 2 minus 3, that is 1 squared, plus 2 minus 1, which is the bottom row, and that's also 1 squared, and then 1 plus 1, which is 2, and then this will be the square root of 2. So you're really adding up the square of the subtraction of the components. So if the 5-component vector, you will be adding up 5 things, right? If it's a 10-component vector, you'll be adding up 10 things because this is the difference of the subtraction of the vector components. And since there are 10 of them, you sum it up, and then you would square and sum it up, and then you will find the square root. All right. So we already talked about the vote. There is an election, and the number of the winning. It's the best way is to have an odd number of make k to be an odd number so that there is always a winning. Someone always wins. But then there is also this interesting idea of weighing, having a weight factor, and this depends on the distance that you calculate. So that you're not just saying that you're close to me. It also matters the degree. We're not just saying you're in my neighborhood. It also matters the degree of the distance, right? So this is more important than this. So in this case, you can break the tie by the weight factor. If you said, well, the distance to this vector, to the negative, is definitely smaller than the distance to the positive, even though they're in my neighborhood, then you could say that this is going to be negative, right? So this is the point of the weight factor, right? But imagine that you just select your k to be an odd number, then you can just simply ignore the weight factor and go by who wins, right? So that would be a very simple model. But even if you're doing that, you still have to calculate the distance anyway, because that's how you determine what your neighborhood is, right? That's how you restrict the amount of data set to consider. And since you have already calculated the distance, you can use it directly as a weight, if you will. You can just weigh the contribution by the distance, right? So for example, there is something called normalization, meaning that you can take any number and you can squash it to a range, 0, 1. So you can take the distance and you can normalize it so that it's on the 0, 1 interval, and you can use it as to weigh the vote. So everyone has one vote weighed by the distance, and this will tell us what the more precise category should be. So this is the more correct answer. But there is a simpler model where you don't use the weight factor, you just count. You just say vote, and that does it. All right. But in the more precise universe, you do use the weight factor, and you want to use a normalized weight, meaning that the distance you would squash that to a 0 to 1 interval. And the way to do that, the easiest way, is by finding the maximum distance and using that to divide every distance you've calculated, since you have to calculate for the entire data set anyway, with relation to the unknown data set unknown data point that you're trying to predict, right? So you calculate the distance of that data point you're trying to predict to every single data point in your data set, and you have a distribution, if you will, of distances. So you can find the max of that distribution, use it to divide everything else, then it will become normalized, meaning that in that sense, the biggest distance will now become 1 and everything else will be less than 1. And you can use that as your weight factor to multiply the votes of the data points in your neighborhood, and this will help you determine more correctly whether the label or the class that your unknown data point should belong to. So anyway, I'm just explaining how to do this weight factor. And the interesting thing is that we're going to actually implement, we're going to do this in class. Nearest neighbor, we're going to actually write the code in Python. So this is just going through the slide, and there will be implementation. All right. So next time when we come back, we're going to continue with support vector machines, and we're going to discuss that. But right now, in the meantime, I would show you how to simply have a simple implementation for nearest neighbors, and yeah. So let me share my screen. Okay. I hope you can see my screen. All right, so this is actually first of all, I will run this code and I will show you what it does, and I will walk you through it, and then we can kind of I will fill in some of the gap for you, and then of course you guessed it, your assignment would be to complete this code and actually have your own implementation of nearest neighbors. Right? So let's run this and see what it does. All right, so the point of this, and this is, I generated this by using matplotlib, pyplot, so it's not a complicated. By just running my code, and if you have a Python IDE and you use pip install to install matplotlib, you can also generate this feature, so it's not a big deal at all. So the interesting thing I would like to see is this right here, is distribution of points. And you being able to essentially run nearest neighbors correctly. And some of the idea would be being able to kind of draw that line, the decision boundary between the points that you're seeing here, or you can color them differently. And this is precisely what I'm doing here. As you can see that these points have different color codes. So instead of trying to draw crazy lines, you can color them. The deep green is, I am going to give you a loan. The light green is maybe, and the very, very light green is no. So yes, no, and degrees of yeses and no. So there is yes, maybe, maybe no, and no. So something like that. So it's a kind of graduated. You don't have to use that many categories. It could just be yes and no, where you have two colors. So you can color red or blue. As you can see that the decision boundary is nonlinear, meaning that there are some points that are deep green, which is yes, and some points on top, which again, I actually haven't done this yet, but this is kind of how a nonlinear decision boundary will look like when you're assigning labels, and it will be kind of scattered around. So so that's that. So let's kind of walk through this code a little bit so that I can show what's happening. So the data is essentially, let's give my screen a minute to recover. I hope my computer doesn't crash. All right, I think it's back. Okay. So you can generate your data by just generating random points. And you can see that this generates a pair of points. So this is a two-dimensional plane. And of course, the question is, the first thing you need to do, right? You need to have a function. The function to calculate Euclidean distance. So now you have your data set, which is a pair of points. So you would have something like this, def Euclidean distance. So, and this is going to take two pair of points. So x1, x2, like so, and then you can find the distance between them. So imagine that I say that, okay, this is a list of int, this is this is just a you don't have to do this. I mean, it's not going to be a list of hint, but it's just it's a guide. Then I could say then that you could have in range of length of x1, right? x1 on x2 is they're going to have the same length because they are vectors in the same space. And then you can have an accumulator because we're doing sum of squares. An accumulator is 0. Then you can say that accumulator loss equal x1 at I minus x2 at I, and you're going to square this. This is what the formula says. All right. So you're going to raise this to the power of 2, and then you're going to add it together. Right? So this is, and we're going to return the square root of accumulator. Accumulator raised to the power of 0.5. Right? So this is your Euclidean distance, and quite frankly, I mean, you don't need you don't need any of this. Would work without particularly defining the type as well. So this is also perfectly fine. And so you need to define Euclidean distance, and and you can also, if you want to calculate your weight factor, then you need to be able to, first of all, you have to calculate the distance for everything on the, so you have to calculate the distance for every point in the data set. Okay. In fact, you need to divide your data set into 2 parts. The one is the training set, which is your example. A set of examples. And the other is the test set. How would you do this? Well, easy. You've generated your random data here. So you can for the benefit of this class, you can select like this. You can write a function to select, right? And I would give you an example. So def get training set, get test set. Right, so this is going to take a list. So this would take my data set, and I would say, so we're going to use the 80-20 rule. So we say we do the same thing for I range data set, right? We want to do that. We want to say if, right? If I modulo 8, or actually so we can calculate K like this. Let's do this. So we can say K equals to, length of data set. Right? And we're going to say that if if our length of data set is less than 20, say 25, we're going to return an empty list. So it's too small. So otherwise, we would say if I modulo k, meaning if you divide by k and it's equals to 0, then I want to add this to my test set. So test set is this. Then I would do test set dot append data set append. And then at the end of this, you can return your test set. Of course, if you're really like if you're really clever about this, you want to return both the test set and the training set, right? You can have a training set here as well. I mean, if you really want to kill two birds with one stone, and of course, if you're not adding to this, you're adding to the other one, right? So you are just doing training set dot append, and you would put data set at high, like so. And then you can return a tuple like this. So you return a tuple of your training set. Right. So and this would be, so you can change this to get training set underscore test set. So the point of this is to kind of show you that you can write easily your Python functions to, so you've generated your code. So this is your data, right? And you have your Euclidean distance, you can get your test and training set. So yeah, so now it's, let me not use K here because it's confusing. Let's use S. Because of K nearest neighbors, you have to determine your K. So you can set K to any number for now. So you can set K to an odd number just for this test. And that's it. And you would now, so for an input in your test set, you have to determine the K neighbors. You determine the K neighbors based on the distance, and then you predict what the label is, right? So of course these data points that you've generated here, they are not it's incomplete in the sense that it would be nice if you could add an attribute to them, right? You can add an attribute to them, and whether it's two classes, yes or no, red or green or whatnot, and you don't necessarily have, I mean, this is easy to plot. This is the point of this, is you have very easy to get it to plot in this way. But anyway, what I would do is I would improve this to add a class, and then I would post this for you so that you have almost all the code. You would have the data. I would show it to you just like I'm showing it here in the plot. And your task would be to finish it. So Please excuse me 1 minute because I have another class that has started. Okay, sorry, I just told them to wait for me. Okay, so I would modify the like I said, I would modify the code so that you have something more reasonable to work with, and it would have a label. Right now, it doesn't have a label, but I usually kind of start from this. Every year, I start from this. This is my as you can see, I have a lot of models here, but this is my base model for nearest neighbors because it has a pretty picture, and then from there I add all the other functions. And it doesn't take time at all. I mean, as you can, I thought about this and I wrote it right away. And this is what you need because you're trying to understand how it works. So you need simple examples. So I would once I'm done with the other class, I would finish up the rest of this code to make it even easier for you. And I will leave some instructions in the code so you know how to take this code and really create a nearest neighbors model in Python. And this would be one of the homeworks for this week. And I would potentially add other things as well. So anyway, any questions before we go? Because I actually have to go soon. Class. Yes, please, man.
So the current proportion between the training data set and the test set is 80 and 20, right? And I wonder why not 50-50 like the one I saw on Cargo. Will they yield different results or it doesn't matter at all?
So the actual selection of your test set from your data set is more complicated than this. It has to be a random draw. I'm not doing that because it's a little bit at a time. So this is not a random draw. A random draw, we have to randomly draw the index of the data point that will be in the test set, right? So, but it's 20% because it's 20% of the total number of data points that you have in the data set. But the selection, you don't do it this way. This is not random. This is completely deterministic. In the real world, it must be a random draw. You randomly draw the index, and then you go and get the data point, that index, and then you add it to your test set. Does that make sense?
Oh, sorry, I was talking about the proportion, like 20% and 80% that will make 100%.
Right. So this is it. There is the 80-20 rule. It's a rule of thumb. It's called the 80-20 rule. There is no reason. It's just a rule of thumb. It's a rule of thumb, meaning that, for example, it is not good to, if you see an old woman, like a grandmother, walking from the market carrying a big, heavy bag, the rule of thumb is you should run and collect the bag from grandmother and take it into the house. So that's like 80-20 rule. It's a rule of thumb. It's just good practice, right? It's good practice. Did that answer your question or I missed it?
Yeah, I was wondering if we do like 50-50 rule, it would yield different results or it doesn't matter.
You could use another rule that makes sense, and if it's a rule that is consistent in the problem space, then your result should be good. So I wouldn't say it doesn't matter. It would, imagine that I am, instead of doing 80-20, I'm doing 75-25. There are some problems where it will matter. It will affect the quality of my result, the generality of my model. As you saw in the slideshow, when the examples that we saw for denying or approving the loan, we don't have enough data actually to answer some questions there, right? So that will happen. So when you don't have enough training data, your model is not as general. So that's a possibility in that sense. But this is not the only one. So if you had 18%, would that be okay? Yeah, that would be fine too. But this is just a rule of thumb that helps. So did I get closer to the answer you were looking for?
Yeah, thank you.
Okay, cool. I can only take one more question. So I think, Maitran, you wanted to say something?
Yes, thank you. I just want to say that I noticed the last homework was posted on LMS in the afternoon of Saturday, which is quite rush for us to get all the homework done. So as I guess that maybe we will get the homework earlier.
I agree. But I knew that the last homework didn't have a lot. So I posted it a little late because it was not as much as the first homework in MongoDB that had a lot more problems to do. And so also you have to know that it's very late for me right now. It's I still have to teach another class, and when I get done from the class, it will be 11 p.m. because I am currently in Houston, Texas. So I will try to post it before I go to bed, but if I can't make it tonight, then I will post it tomorrow morning. But
yes,
yeah. But I won't give you work that you cannot do. I will give you just enough to keep you busy, but not so much that you won't be able to complete. Does that make sense?
Yes, I would very much appreciate if I does not have to spend my weekend doing homework.
I don't know if you won't spend your weekend doing homework. You might have to, but it won't be too much.
Yes, thank you.
All right. Okay. Well, bye, guys. And
Professor,
okay.
Are we just doing the class test and that's it? Or
are you saying that is the homework just going to be this? Nearest neighbors? Oh, sorry. That was from my other class. I'm sorry. Okay. Bye, guys. See you next time.
Yes, goodbye.